Our next speaker is Mark Rica of the USGS Western Ecological Research Center. He comes to us from the Dixon Field Station in Dixon, California. So, Mark?
All right. Thank you, Christian. Let's see if I can see this here. Okay. So, Pete really kind of set the stage for this next talk coming up here, where Pete basically described the process by which Pinyon Juniper encroachment influences sage grouse habitat selection and ultimately consequences to fitness. Here we're going to talk about basically how a behavioral mechanism behind those processes, in particular how PJ drives potentially sage grouse to have more riskier movements. And I want to point out that this work actually was led by Brian Prohaska. Brian was a master's student in Pete's lab. And so basically, this is all kind of a large team effort. And Brian did some amazing modeling here that I'll be trying to do my best to describe. And also, Pete kind of alluded to kind of an example where we want to, basically kind of give managers an idea, given that we know these adverse effects that PJ has on sage grouse, how can we then basically put this into action and hopefully hope to guide managers where best to put these treatments. So we're going to talk a little bit about that at the end as a little bonus. And I guess I'm going to trick here, but yeah, it looks like the video, well, let's see, maybe it will work. Let's try. I'm just going to hit it and see what happens. Hey, it works. Okay, cool. I got lucky. So what Pete unfortunately wasn't able to show you was that the video that didn't work was basically a population of our birds in the bi-state moving across a PJ encroached landscape. What I'm going to show you here is one single bird, GPS marked bird, with locations taken one per every hour during the daylight time. And then this kind of cloudy sort of stuff you're seeing there, looks like green clouds. That's actually our PJ map that we've actually just done neighborhood analysis on. So the light areas are basically phase 1 and the darker areas are phase 2 and 3. And what I want you to kind of point out here is, if we get it going again, if I'm lucky, yeah, here we go, is look at the amount of space between those points. And essentially here they're crossing a lot of PJ, a lot of distance between those points, kind of stopping here and there, a little stopping in some phase 1. Slowing down here in a wet meadow complex, hanging out, maybe on the edges, but more concentrated use. Large, fast movement across PJ, coming in again into a more of a sagebrush area, and then bam, just making a really, really fast movement across a big expanse of PJ here in the bi-state before settling down. There's just a little bit of stop over here and there before settling down into more of a sagebrush ecosystem. And this was over just a 1 month period. So that gives you a good idea of basically kind of the hostile matrix that sage grouse encounter as they're moving across this landscape and the different behaviors that they have to do in order to traverse it and ultimately survive. So our ultimate basic objective with this research is, basically first to just look at how do sage grouse movement rates vary as a function of the probability of Pinyon juniper encounter. And unlike the previous analysis, we're going to look at this by age class. We're going to look at this according to whether or not birds are juveniles, basically less than 1 year old, yearlings, or adults. And we then equate that in terms of in terms of how much they've experienced, assuming they've survived to adults, what they've learned about their environment as they've got to get older. And then given this modeled pattern that we see, we're then going to relate this back into fitness consequences and see how that actually influences their survival across these different age classes and how they may interact differently. So the example Pete described was specific to the bi-state. This area, again, I'm just going to point, you can see it, down on the lower left corner there. For this analysis, we actually we have over 12, now we actually have 15 study sites across the bi-state, northeastern California and Nevada. Been doing this for 4 or 5, in some cases like 8 years or so. So we have a really large data set. We have over 233 GPS marked adults, yearling and juvenile sage grouse over the years that we were able to use this data from. And with this, we're getting about 10 to 13 locations per day, daylight hours, and that's over 280,000 locations. So we have a really, really powerful data set in terms of high frequency location data. And then we can then couple that in terms of this new high resolution mapping that Pete described using the object-based image analysis feature analyst sort of program, to where we basically can have a good depiction of basically in a spatially explicit fashion what that risk in terms of PJ, what it looks like. And so we have this great data. So we need to have some analytical tools, both spatially, or spatial tools, statistically, to be able to make some sense out of it. And I don't want to get too much in the weeds in terms of stats here, because it can get pretty complicated. But what I want to just show here is this depiction here. The green pixels represent Pinyon Juniper mapped at about 1 meter square resolution. And then the blue circles and the red circles with little lines in there, those are they're essentially grouse home ranges. They're derived from Brownian bridge movement models. It's a technique used to calculate basically home ranges for high frequency location data. And the take-home point I want you to get here from is essentially in the upper corner where it's all kind of brown or sagebrush. All those Brownian bridges look the same. They're all kind of circular, kind of in a big sort of blob, kind of tight. However, then you basically get one or two birds that peel off over here, and they kind of, the bridge starts to take a different shape. It starts to get a little more elongated, meaning they're moving faster. And then when they encounter PJ right here, it takes that different shape again. It spreads out until they get out of that PJ, and then it opens up again. So what this is giving us insight into is really distinct behavioral states that these birds are doing, whether they're moving fast or moving slow. And then to do this analysis, we actually have to break these things, we actually have to quantify these into actual distinct states. And we use a process called behavioral change point analysis to do that, which essentially breaks all those location data up into basically distinct behavioral states. And then we actually calculate a Brownian bridge for each one of those, and then do that across all the birds and sum them up. And then relate that to the probability of Pinyon Juniper encounter. And I'm going to show you how that works here in this next sort of slide, kind of walk you through it in terms of the basics of it. So what we have here, this is showing essentially, again, the green pixels are Pinyon Juniper, and then we have two Brownian bridges that we've calculated for a single bird that are indicating of different behavioral states. This one here highlighted with the red rectangle, this is a bird that's moving through a PJ encroached landscape. It's got kind of a faster movement, so there's a higher diffusion coefficient, so it's got a lot more uncertainty to it, a lot more spread. In contrast, once they move out of that PJ, we have this really tight little kind of circle, meaning that the movement is slowed down a whole lot, and they're really more concentrated and a lot more certainty to where they're going to be. So what we can do then is I'm just going to show you for the fast movement rate. We calculate that Brownian bridge for that one behavioral state, and we're going to do this across a whole bunch of Brownian bridges. And then we intersect that with an underlying PJ map, where essentially a PJ, if it's present, we code it as 1. If it's absent, we code it as 0. And then we take the product of basically those pixel values in the utilization distribution and multiply that by that underlying PJ map, and we get a probability of PJ encounter. So essentially, if they have a high probability of use and the encounter and the intersects of 1, that increases the probability. If it has a high probability of use, encounters a 0 for no PJ, that lowers, there's no probability. So we then sum all that up to basically get the overall probability for that bridge, and then clip it to basically the 95% home range, and then sum all that across all the birds and all the UDs to give us basically our risk or probability of encounter with those states and movement patterns. So basically, in terms of what we found, just pretty much I'm going to describe three main findings from this work that kind of tie back into what Pete described previously. First here, this chart is showing the probability of Pinyon Juniper encounter on the y-axis, along with the different age classes on the x. The juveniles are the green, yearlings are orange, and adults are purple. And the point here is essentially that adults are about 2 times more likely to encounter Pinyon Juniper than the younger age classes. You'll probably move around the landscape a bit more. However, when we flip this thing around and we put the probability of PJ encounter on the x-axis, and then look at the daily movement velocity on the y-axis, and look at that in relation relative to the different age classes, again, the colors are the same. See a couple of things, and the first is that all the age classes move exponentially faster as they encounter PJ. So basically, the more PJ they encounter, the faster they're going to move. And that's important later on for fitness. And the other thing is that the juveniles, they tend to be a little more skittery, and they tend to move disproportionately faster as they encounter more PJ compared to the yearlings and the adults. Basically the difference is smaller at the lower end, and it's greater at the upper end. So kind of an interaction going there. So that's all. That's pretty cool stuff. But really the bigger question is, what does this mean in terms of fitness and survival? And so what this graph is showing here is kind of complicated, but I'm just going to highlight some of the main points. On the y-axis, we have basically the annual probability of survival for each of the different age classes. And then the upper right-hand, or upper axis, kind of the upper x-axis, is Pinyon Juniper encounter going from low to high. and then we have movement rate down on the bottom going from low to high. And what we find is that if we look at how those two predictor variables explain variation in survival, we find that the effect of Pinyon Juniper encounter on those survival rates it was not consistent. It varied on basically how fast they moved, but that was only for particular age classes. In other words, that strength of that interaction was dependent upon those age classes. And what I mean by that is that all age classes are basically very likely to die when they're moving very fast and they're encountering a lot of PJ. And to illustrate that, just kind of look at this bottom corner here with high PJ encounter and high movement rate. And basically the probability of survival is pretty much 0. However, for yearlings, what's going on here, or excuse me, for juveniles, basically it doesn't matter how fast or slow they're going through a PJ encroached landscape. They're going to go fast, they're going to go slow, they're going to die. Adults, on the other hand, and to a lesser extent juveniles, they actually might be able to mitigate that risk. For the few individuals that just do this, most of the adults are going to be moving fast, but there's going to be some individuals that actually maybe they might be able to move a little bit slower through these PJ landscapes. And what that's going to equate to is potentially reduction in their mortality risk and an increase in survival. So this is what we did. We basically kind of put all these, there's a lot of information to digest between Pete's talk and this talk. But I think this summary kind of flowchart just basically kind of illustrates what a sage grouse has to decide when they encounter Pinyon juniper across the landscape. And they have a couple of decisions to make. The first decision is whether or not I'm going to avoid it, particularly cover class 1 like Pete just described. If they avoid it, basically they have a very high likelihood of survival. This is the same graph that Pete showed, and essentially a 20% increase in survival probability with very tight, essentially, confidence intervals in those Bayesian. So, it's a smart decision to do if you're a sage grouse. However, there's a lot of PJ out there. Sometimes you can't avoid it. So if they are going to actually use it or actually traverse across it, they have two behavioral choices to make. The first one is essentially if they decide to move fast, which is probably the most common. And if they do this, we know because of that faster movement, they're going to die. They're most likely going to die. And that's because these are, they're cryptic animals normally, but if they move around a lot more, they're going to be more susceptible to visually acute predators such as raptors most likely. And this is also the case across all the age classes, adults, yearlings, and juveniles. But if they decide to slow down, they actually might, that survival risk might actually be lessened or mitigated. And we only found this for adults and maybe to a little lesser extent for yearlings. And so maybe what this means is that as a bird becomes more experienced in their environment, they may pick up on some of these environmental cues that says, I need to slow down when I'm in this sort of PJ environment. So basically, this is kind of one mechanism behaviorally that kind of explains some of the processes that we saw earlier. So the second part of the talk, I kind of want to shift gears a little bit. We've got a lot of body of evidence, the last couple talks that are going to be coming up here that basically describe, the negative ramifications of having conifer encroachment on sage grouse as well as prairie chickens. And what managers kind of need is really they need tools to identify areas that are going to be most suitable for conifer removal, particularly because these are relatively expensive. And I'm going to provide an example from the bi-state distinct population segment that Pete talked about earlier. This, many of you know, probably this DPS was a candidate for listing a few years ago. However, it was removed for listing for a couple of reasons. One reason was because a lot of money, about $42 million, was allocated towards sagebrush restoration to bi-state. And a big focus of that, about almost over $30 million, was focused on conifer removal treatments. And so what we basically, Pete described essentially, he showed an example of, basically, forming these polygons, basically proposed areas to cut based on, the habitat productivity, R&R, those sorts of things. So this is an example where essentially managers are kind of doing that and developing a candidate suite of Pinyon juniper treatment areas. But then we also needed to find a way of quantitatively ranking which ones might have better benefits to sage grouse relative to the others, so we could allocate resources most efficiently, and all rooted in sage grouse ecology. And so I'm going to focus in on this area here, circle, to kind of give you an example of kind of how the process works. And we're constantly working on expanding this framework. So in this example here, this is one proposed treatment polygon, and we first classify those PJ classes into their corresponding cover classes or phases of encroachment. We're going to primarily focus on what happens with phase one. So we have our map here for PJ. And then what we do is we generate, here on the right-hand side, we generate essentially a habitat suitability index that's spatially explicit across the entire bi-state. That's given a whole bunch of habitat variables, land cover, distance of stream, topographic variation, PJ, those sorts of things. And essentially what it is a heat map. So when it's blue, it's relatively poor habitat. When it's red, it's pretty good. It's highly suitable habitat. And we do this prior to simulate tree removal. And when we do this when we get this baseline habitat suitability index, what we see is this area is pretty lousy. It's all pretty much blue, with the exception of kind of a little yellow area here on the bottom. So then what we do in a GIS framework is then we simulate the removal of that cover class 1, which is these hashed areas. And then we also simulate restoration of the understory, because now there's no longer PJ on top of it. We can let it turn back into be sagebrush or whatever the dominant shrub type might be. We then regenerate that habitat suitability index, or actually it's a resource selection function, but basically a measure of habitat's suitability with that cover class 1 surface removed. And then we calculate the difference between the simulated, post-removal or conifer removal landscape with that baseline. And now we see a dramatic increase. We see a lot more of this areas lit up in red. So we see we've got a really, a dramatic increase in potential habitat improvement for sage grouse with this site. This also might be a site where maybe it might be 30 miles away from a breeding lek. And sage grouse are, especially in the bi-state, are really concentrated closely to these breeding centers. So we calculated a space use index, which is essentially a product of the lek density, or the average of basically the density of leks, abundance of birds, and probability of use relative to distance to lek. And then we multiply that change in habitat by that space use index. So we see actually it goes from smaller to actually bigger. Then what we do is we basically sum all those values up across all those pixels, which is now our ecological currency for ranking these proposed treatments across our proposed treatments. And we actually call this a grouse benefit index, for lack of a better word. And then we do this, we can adjust it by cost. And what I want to show you here is just a couple of things. These are the same treatment polygons, and the red ones are basically the ones that provide the best benefit for grouse. The blue provide the worst. And the main point here is that the top four treatment polygons, even though there's only 4 out of 27, they comprise over 60% of the cumulative benefit to sage grouse across all these treatments. So really big bang for the buck for just focusing on four of these treatments. And the bigger point too is if we look at in terms of cost perspective, the top ranked polygon versus the bottom ranked polygon had the same amount of PJ cut, same amount of acreage, or same cost, but the difference in terms of the benefits to grouse was over 4,800 times higher. So really a big difference. And then we can also do things like integrate this with resilience and resistant measures and other sorts of both demographic and environmental matrices. And this has all gone into a lot of planning documents, both in the bi-state as well as now working across the Great Basin. So just to summarize up here, I think I have about a minute left here. The take home is we have an increasingly large body of work that quantifies the effect of Pinyon juniper on sage grouse population ecology. We know about basically broad patterns from Baruch-Mardeau and others, which basically describes the overall impact of Pinyon juniper on lek persistence. That's basically the overall demographic pattern. We now have some better insight in terms of the processes that may be driving those patterns in terms of individual variation and PJ avoidance, and those fitness consequences, essentially going into these ecological traps, highly productive habitats, but have sporadic, sparse trees that raptors can perch on, and lower survival risk. And then lastly, we have some information on the mechanisms, where essentially how, when birds encounter these PJ encroached landscapes, how their movements are altered, and how that varies with fitness, or how that impacts their fitness, and how that varies with age. And then lastly, we can then take all these metrics, given all these effects, we can then develop conservation planning tools that can help provide managers with tractable information to make good decision points for as a first cutting point. So with that, that's it.